Great. There was just enough time for me to clear the blackboard. So as promised, I'll keep going with the 3D TI, and that's nicely complementary to what Joel was talking about, because again, I'll try to give you an explicit construction of that phase. So, however, so as you heard from Joel, the whole thing is protected by time reversal symmetry, which makes this theta invariant quantized, for instance. And here, however, I would like to take, for the sake of this construction, an slightly enlarged symmetry space. And then later on, we'll see which of these symmetries are actually needed to protect, for instance, the Dirac surface states, and which are just a vehicle to get there, if you wish. And so what I want to assume is that we also have a chiral symmetry and inversion symmetry initially for this construction, but we'll break that, or we'll be able to break that eventually. And so the object that we want to use to construct this 3D TI is a Sushi-Hiccup chain. So that's why we worked on the Sushi-Hiccup chain so much. And more precisely, we take a Sushi-Hiccup model. So far, we've looked at that as a spinless model, but we want to basically take two copies for spin up and spin down, and such a system would be basically like a 1D system, right? That's kept, and then at each end we would have now a pair of states. Yeah? So you can really think of the model that we had before, but you just take two copies of it. One get all the electrons get a label up, and the other one all the label get a label down. And now this end state here is of course protected by the chiral symmetry that we have. So it's like a Sushi-Hiccup chain with two end states. We saw that there was an integer classification, but at the same time we now have a t squared equal to -1 time reversal symmetry. So the end of this Sushi-Hiccup chain is going to be a Kramer's pair, right? As well, under this time reversal symmetry. So one will like have spin up and spin down. And otherwise, this 1D chain is kept. So this will be the building block for our 3D TI. And I remind you that this has inversion eigenvalues now, the band structure. That was our last way of characterizing the topology. So now we have two bands which are actually degenerate everywhere because of time reversal times inversion. Along this one momentum, in the topological phase, you would say that inversion eigenvalues are minus and minus here and plus here. Yeah. So this Kramer's pair, if you wish, in the Brillouin zone now is an inversion minus eigenstate at k equal to 0, and the plus eigenstate at k equal to pi. So these are the inversion eigenvalues. Okay, and now I want to construct a 3D system out of that, and I'm not going to use equations, I'm just going to use your imagination. So let's consider a 3D Brillouin zone, and I'm just going to say what the Hamiltonian is supposed to be in some places in this Brillouin zone. So, so let's say this is Kx, this is Ky, there's Kz. And now in the Kx, Ky plane, there are four inversion and time reversal symmetric momenta at Kz equal to 0, say. These are the ones that I label here, 0, 0, pi, 0, pi, pi, and 0, pi. And now what I want to do is I want to use a Hamiltonian which is equal to the Sushi-Hiccup model along the kz lines in this system. So, for instance, along this line, I want h equal to h Sushi for Heger. And the same is true along the other lines, here, here, and here. And everywhere else, I just want to interpolate between these Sushi-Heger chains. And I can do this. I mean, you have to believe me that I can do this, but there is not much of a local restriction on what the Hamiltonian is everywhere else. The only restriction is that under time reversal and inversion, it needs to be symmetric, but that really just relates, the Hamiltonian at different momenta to one another. And I just want to keep chiral symmetry in this business. Okay, so suppose I have a Hamiltonian that's defined like this. So it interpolates, so H interpolates between topological and trivial SSH chains. Okay, so imagine I have such a Hamiltonian. And now we just want to think about the bulk boundary correspondence, and the easiest thing for such a system is to look at the surface. So we want to now look at this 3D system with periodic boundary conditions in x and y direction, but open boundary conditions in the z direction. And then we can ask ourselves, what do we know about the surface spectrum of this model, right? And so, what we know is that let's say we plot the energy as a function of kx, for instance. I could have chosen ky. Energy. So then we know that let's say for ky equal to 0, just to have some cut. We know that at kx equal to ky equal to 0, we have the spectrum of a Sushi-Heger chain. That's topological, actually of 2. So we would have, a lot of bulk states. But then there are also two, just on one surface, there are two surface states, right, which are these end states here, yeah? So there's a Kramer's pair of these surface states exactly at this momentum. And then if we go to kx equal to pi, this would be 0, this would be pi. We also know the spectrum. It's the one, again, of the Sushi-Heger chain, but of the trivial one. So we don't have any surface state. So we just have this spectrum. And now the observation is that if you count the number of states, let's say there are n states here and n states here, then there must be n minus 1 here, n minus 1 here, and there are 2 states here, right? Because, this is now, all the eigenstates of the chain. So it's if it's n sides long, I have to have as many states as I have sides, or yeah. And so now the question is, how can I interpolate between this spectrum and this spectrum in a way that is compatible with time reversal symmetry and with chiral symmetry? So time reversal, of course, tells me something between k and minus k, but what is important is the chiral symmetry, which tells me that I have to have a spectral symmetry as well. Let's say the following. What could I do with these 2 states? I could, of course, think of putting them both, going up there. But then I would be off with my counting, right? Because then I would have n plus 2 states here, and here n minus 1. So the n and n I can only get if I let one state go up and one state go down. Yeah? This is the only consistent way of connecting these 2 models. And so you see what I get here, and then of course the bulk states, they'll also be connected in some way. but you see what I get is this, this linear dispersion, or whether it's linear or not, I can't really tell, but definitely it's the gapless surface state that Joel was also mentioning. So this is the surface Dirac cone. Yeah? And now, of course, we've used chiral symmetry, inversion symmetry, time reversal symmetry to construct this. But you can ask what is actually protecting this Dirac cone. And the only symmetry that's really relevant for this is time reversal symmetry, because as long as this Kramer's pair here is protected from hybridization due to this connectivity that you have, this spectral flow between the conduction and the valence band, you cannot remove by any surface perturbation that is time reversal symmetric, you cannot remove this state, right? You can move this up and down a little bit, this whole construction, but it wouldn't go away. So this surface Dirac cone, like a Hamiltonian for that, would maybe be kx sigma y minus ky sigma x. And time reversal in this case is the usual suspect, I sigma y times complex conjugation. So this thing remains massless as long as you preserve time reversal. And so we can basically think of the inversion and the chiral symmetry as just vehicles that we used to get to this state. But it's convenient still because there is a very nice expression for the invariant. Yes?
But I have a question for it. I mean, inversion and the chiral symmetry sort of ensure us that we have these zero states at zero in the first place. So we wouldn't have them.
So suppose you have constructed the model like this, and now I allow you to do perturbations which are breaking chiral symmetry and inversion symmetry, but do not break time reversal and do not close the bulk gap so that I don't have a topological phase transition. Then the point is that this cone cannot go away, despite I allow you all these perturbations. Yeah?
The point is not that sort of you could start without them and only time reversal.
No, yeah, you wouldn't. I mean, I haven't rigorously shown that part, but you wouldn't be able to do that. Yeah. Mm-hmm.
And getting the cone was a connectivity argument.
Yes.
But that doesn't tell me anything if I have a linear dispersion.
No.
I could construct it.
Yeah. So now you could ask what kind of Hamiltonians can you write down that are time reversal symmetric? And since these are Kramer's pairs, basically you would see that the lowest order term would be linear, or you would have at least an odd power. So you could come with k3, k to the cube, and so on, but you wouldn't work with this quadratic. You couldn't convince yourself from symmetry arguments that you couldn't have a quadratic touching. Okay, so now I want to, however, dwell a little bit on the inversion symmetry because it gives us a much easier expression for the topological invariant compared to the one that Joel was mentioning. So the theta is actually hard to compute in a practical way. If you have a lattice model, you have to differentiate your eigenstates to get the Berry connection, and this is horrible because usually you don't have a smooth gauge. So if you have a system that in addition to time reversal symmetry is also inversion symmetric, let's remember our inversion eigenvalues here. They were minus, and then there's somewhere kz equal to pi. So there were minus 1 here and plus everywhere else, let's say. Oh no, let's say minus, I think. What was it? Minus, 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 minus. So there is this one plus, and all the rest are minus ones. And the formula that is giving the topological invariant is the product over all occupied bands. The product over all time reversal invariant momenta, called trim, of the inversion eigenvalues, and you count one Kramer's pair only once. Yeah? So these are inversion eigenvalues. And you count every Kramer's pair once. And this product can give you plus or minus 1. So this is so-called Foucault, so obviously named after Foucault, formula for inversion symmetric TIs. And so if this thing comes out to be a minus 1, which would be the case here, right? Because you have 7 times minus 1 times plus 1 eigenvalue, then you have a 3D topological insulator. And the inversion symmetry is just a convenient way of getting to the invariant. It's not necessary to protect the Dirac cones. And in that sense, people also sometimes talk about the band inversion because at some point, right, at one of these trims, or an odd number of these trims, you should have an inversion of the order of the bands with plus and minus eigenvalue. Yeah? Okay, so that's Ka. That's A element occupied bands, sorry, and K element the trims, time reversal invariant momenta. Okay. Good. So that's that. How am I doing with time? Okay. Now we come finally to topological crystalline systems. So we want to find, or we want to discuss now systems which have topological boundary states that are protected by crystalline symmetries, like inversion, rotation, stuff like that, could protect topological boundary modes. And such crystalline symmetries are always, they are unitary and they are non-local, so they are mapping parts of your system to other parts of your system, right? Like inversion does. So, and I'm going to be, relatively short. I have to be short on that, so I'll basically give you one example of such a TCI. So these have boundary states protected by crystalline symmetries. And of course, it's important that the boundary is also invariant under these symmetries. Otherwise, you wouldn't have the boundary states. Needs to respect symmetry. So that's, of course, also true in the topological insulator case, if you wish, because you want to have time reversal symmetric boundary, but it's maybe a more generic situation to have than having like boundaries that are invariant under rotation or under mirror. So you have to think a bit harder whether this really happens. So so the one case that I want to discuss is in 3D. 3D systems where mirror symmetry and so we're going to look at MY, for instance, and time reversal symmetry protect states. So the combination of mirror and time reversal, that's the example I want to look at. And the upshot will be that in these systems, unlike in the topological insulator, I can stabilize more than one surface Dirac cone. So in the topological insulator, it's of course a C2 characterization. Either I have one Dirac cone or I have 0. Here we can have multiple Dirac cones that are topologically protected by the mirror symmetry. So how does that work? Again, it's most fruitful to look at the Brillouin zone in the 3D bulk first. And think about what mirror symmetry does in this Brillouin zone. So So if we have this mirror symmetry my that sends y to minus y, it also sends ky to minus ky, and as such, it leaves two planes in this 3D Brillouin zone invariant. The one at ky equal to 0, and another one at ky equal to pi. Yeah. So on these two planes, all the states are mapped back to themselves under the mirror symmetry. And that means these states, the Bloch states, can be chosen to be eigenstates of my. Okay. So my, of course, so let's say we have a spinful system, my squares to minus 1. So it should have eigenvalues plus or minus I. So it has two eigenspaces. And let's say then we separate the Bloch wave functions of the occupied bands on these planes into these two eigenspaces. So we have a set of U plus, let's say, K and band index. And then we have another set of U minus Ka. Yeah? So we have all the occupied bands on this plane split into two sets. And now the nice thing is, due to the separation, we can define two different Berry connections and two different Berry curvatures for each of these subspaces. So we can say we define this F plus minus of K Oh, actually, that's now, yeah, no.
So it is a simple,
Yeah.
simple question. So y plus minus I not plus minus 1, why y squared to minus 1?
Because we have spinful electrons, right? So inversion is always not acting on the spin. And then inversion times my is a C2 rotation. That C2 rotation should enforce a minus 1, right? Sorry, C2 squared should enforce a minus 1 on the wave function of a spin 1/2 particle. So that's why also spin, a mirror has a minus 1 when it's.
So what do you mean by the boundary with respect to symmetry? Should it be invariant in the direction of symmetry or just compatible with the symmetry?
So it should be, I don't know what is the difference between invariant and compatible?
Like, for instance, inversion does not act, so it acts as it changes every point in the space, but you can have like boundaries that are compatible with the inversion.
Okay, so here I would look, first, okay, we will actually look at both cases, but now I want to look at a surface, a 2D surface that respects the mirror symmetry. So I would eventually look, for example, at this surface, which is mirror invariant. I guess that's, in your definition, invariant? I mean, that's what I want to look at, okay? Yeah.
So you require the bulk to be gapped.
Yes, bulk is fully gapped, yeah.
So actually this is relevant for the previous case as well. Does that require additional constraints on the symmetries?
No. The fact that the bulk is gapped is actually really, that's just an energetic statement. It doesn't, I mean, okay. There are some very curious symmetry combinations which require for certain fillings that the bulk is gapless. These are some sort of symmetry enforced, filling enforced semi-metals and stuff like that. But leaving these special cases aside, generically I can, I'm assuming I can make an insulator with these symmetries, basically, yeah. Right. Okay, so what I want to say is that I can define, I'll just write it schematically, I can define the Berry curvature now for each subspace separately. And for that reason, I can also define a Chern number on these planes. So on these ky, on ky equal to 0 or pi plane, I can define a Chern number for each of these subspaces, right? So let me call it C plus minus. That would be the integral over kx and kz of trace of f plus minus xz of k. Okay? So I have these Chern numbers now. And why is it meaningful to, or why do I need this grading to even talk about the Chern number? The reason is that because of time reversal symmetry, the total Chern number has to vanish. Yeah, it's a time reversal symmetric plane. We know we would have a Hall effect if it wasn't vanishing, so that better not be the case. So C plus C minus, which would be the total Chern number. Joel told you that the Chern number is additive. That has to be 0. But that does not mean that C plus and C minus individually are 0. It's a little bit like with these spin Chern numbers that Joel mentioned. We can now define what's called a mirror Chern number, which would be C plus minus C minus over 2, or yeah, and this can be non-zero. Okay, and that would be our topological invariant.
You mean the topological invariant on the whole, no?
It's yeah. I mean, it depends. Yeah, it's of course only defined, or you only need to know the states on this subset of the Brillouin zone. But it's after all, it's a topological invariant for the full 3D system.
Yeah, but maybe something in the not NY symmetric planes can mess with this invariant, right? No?
How should it? I mean, I just need the MY symmetric planes to define it. So how should it change if these states remain the same, right? No, and so it's. I mean, I've shown that it's an invariant and it's defined for the system with this symmetry, so it's perfectly fine, I think. Yeah. So now we can think about the bulk boundary correspondence, and for that, let's, for instance, look at let's look at the surface Brillouin zone. So here's our surface. It's My invariant. So we have ky and kz, let's say. And now there are these projections of these mirror planes, which are these mirror lines in the surface Brillouin zone. Now, what do we know about the spectrum of the system when, for instance, the mirror Chern number is 2? Let's look at that case. What would we know? So let's think about our intuition from the quantum Hall system. What this means, and of course on this line I still have these two separate subspaces, is that in each subspace I have a Hall effect with Hall conductivity 2. So when I would look at the spectrum at the boundary as a function of kz for, let's say, ky equal to 0, or yeah, let's say ky equal to 0, the energy spectrum, what I would find is, if I just draw for one subspace, let's say for the plus subspace, I have a Hall effect with Hall conductivity 2, so I have a bunch of bulk bands, and then what I know is that I have to have two chiral edge states in this surface Brillouin zone, right? Sort of in this 2D slice of the surface Brillouin zone. That's what that would be the Hall effect states. That's the plus subspace, plus I subspace. And now for the minus I subspace, of course, it's just a time reversal of this one, right? So the minus I subspace is basically also having a Chern number, but -2, so it has to have two modes that go in the other direction. And the whole arrangement should be time reversal symmetric. So these two, okay, it's not perfectly drawn now, but they should be at equal distance, these two crossing points at equal distance from the origin, right, in KZ. So, so one observation now is that these crossings, they are protected by my, right? Because I could in principle hybridize these crossing points, but that would require coupling a left mover in one mirror subspace with a right mover in the other mirror subspace, and that explicitly would break mirror symmetry.
Sorry, a question. So you define the Inversion number for its plane, but is there any reason to be the same for the two planes?
No. So, okay, let's say here consider the case of Cm equal to 2 on Ky equal to 0, yeah? So I'm looking, yeah, no, they don't need to be the same. They're completely independent quantities. Okay, so this is protected crossing. And now if you think about how this, of course this is now at Ky equal to 0, but if you think about how this dispersion would continue if you go to finite Ky, then there's no local constraint. You can hybridize these states. And that means that you get two Dirac cones on the surface, right? If you extend it to the full 2D Brillouin zone, you would basically get a Dirac cone here and another Dirac cone here, yeah? So these are two 2D Dirac cones. Okay? And so you see that this mirror Chern number in the bulk tells you how many Dirac cones you have on the surface. They're protected by mirror symmetry.
Would you think of a situation where you have a C plus that is, say, 3 and C minus that is -1, or is that prohibited by the symmetry?
It's prevented by time reversal, right? Because of this sum rule. I mean, in general, it's possible, but not in a time reversal symmetric system. If you break time reversal symmetry, that can happen. Mm-hmm. Okay, so Dirac cones on the surface of this TCI, they are protected by mirror symmetry. Yes?
In the case of spinel effect, when you have panels like this of transmission to just flow so to spin, what is the analogous in this case?
I don't think there is actually any transport signature, at least I'm aware of. Because you see, this is a 2D system, right? So there is no conserved, I mean, not even if you were, there is no conserved spin, right? I don't think, so the only thing that you could now argue is that maybe, depending on how you could open a gap here, that you get a quantum Hall effect with like 1 on the surface if you open the right gaps, if you break time reversal and stuff like that. But in terms of spin, I don't think there's any conserved currents or spin-like things. I mean, you can always define some sort of Welle quantum numbers at low energies if you are into that sort of thing, but yeah. Okay. I should also mention that why did I go to Cm equal to 2 directly? The Cm equal to 1 case is, of course, a topological insulator at the same time because it has one Dirac cone on the surface, right? So that's why I just went to the more non-trivial example. And in terms of materials, maybe that's relevant. There is a beautiful realization of this in tin telluride or lead-doped tin telluride. So this is kind of the poster child of TCIs in terms of materials. Okay. And now I have something like 25 minutes, and I want to talk about higher order topological insulators in this remaining time. Let me first give you a quick intro to what that means, and then we can use some of this material to get to an example. So here again. So far, we've always looked at systems where the bulk boundary correspondence is such that you have a bulk that's d-dimensional, and then you look at the d-1 dimensional boundary, and we see whether or not there are gapless states on this d-1 dimensional boundary. So for instance, here, 3D system, 2D surface, and then we look for surface states. Or in the Sushi for Hiccup chain, 1D system, 0-dimensional boundary, is there something? In this concept of higher order topological insulators basically asks, are there systems where it's not the d-1 dimensional boundary, but the d-2 dimensional boundary that could carry a mode. So the picture here could be, for instance, a 2D system which is gapped in the bulk and on the edges, but has 0-dimensional corner modes that are topologically protected. That would be the simplest example, and that was actually the first one. But we can also think about two ways of doing this in 3D. I could think of a 3D system gapped in the bulk, gapped on the surface, but it has some sort of states that are propagating along the hinges of the system. So maybe they do something like this, and they are gapless and topologically protected. Okay, so this would be another option. And of course, there is exactly one more in the 3D world. That would be a 3D system which is gapped in the bulk, on the surface, on the hinges, but has corner modes on all the corners of, say, a cube or so. So the general idea is to find topologically protected modes on higher order boundary components. And the general statement is that this always requires spatial symmetries to be protected. So these are always a subset, if you wish, of TCIs. Okay, so that's the general setup. Yes?
So I'm always a bit puzzled about this statement that you require spatial symmetries, because when you read the breakdown, usually the modes survive, right?
Right.
So you see this as like a small perturbation away, and therefore it's
So it depends a bit on the rules of the game. So what I would like to say here is that these modes are stable against any perturbations to the boundary. So for instance here, I would like to do any perturbation, gap closing or not, on this, that symmetry preserving on these edges, and still want these corner modes. If I relax that condition, but I don't want to touch the bulk, obviously, otherwise there can be topological phase transition. If I relax that condition and say, okay, I actually want to, I have a system, it's gapped here, it's gapped on the edge, and now I want to fiddle with it, then you can do with a weaker statement here. Yeah. That's correct. Okay, good. So what we'll focus on here is two examples of this type. So 3D systems with some sort of hinge modes that are propagating, and I have like 10 minutes for each of them. That's generous. So the first one we can construct from our TCI that we know already here, and what we're going to do there is the following. So we look at that surface, and so let me draw it again. So we have this surface with these surface Dirac cones, right? So there is the mirror symmetry, and we look at that surface. And now think of this as the surface Brillouin zone, yeah? Okay, so there is, I don't know, this is maybe a spatial direction, but the other ones are what could that be? KX, I don't know. So there are two Dirac cones here, as we showed. And now I want to consider a small perturbation to the surface. I want to make a little kink in the surface, but retain mirror symmetry. Okay? So I want to make a but keep my. So I don't know how good I am at drawing this now. It's like a roof. It looks like a roof of a building, right, of a house, something like this. And now we have two surface planes that are touching each other at this hinge, yeah. And now on each of these surface planes, of course, I've broken mirror symmetry, right? Just weakly, but I've broken it. So locally on this surface, if I look at the surface Brillouin zone, I would have these two Dirac cones, but they could now be gapped out because mirror is weakly broken, right? So let's say this is a gap M due to mirror breaking. And now I look at this, the Brillouin zone on this other side of this roof, and I would find, of course, the exact same spectrum. Yes?
Or you said mirror breaking, you get my, which mirror?
No. So this is I keep my in the whole structure, but if I look at the electronic structure of one roof side, then mirror, there's no mirror. If I was, you know, I'm looking at the Brillouin zone on this side here, so basically I'm thinking of this as actually an infinite roof, yeah? Then I would say this, on this one, mirror is broken. Just the combination of the two parts of the roof as a whole keep mirror. That's how I want to understand it. So the other guy has the same spectrum, massive Dirac cones, but because of mirror now, because the two sides are related by mirror, I have to have a gap minus m. Yeah? So here I have minus m, here I have plus m in each Dirac cone. And now we can use our knowledge from the first lecture today, where we have now a Dirac cone which is changing the sign of the mass. And we know that there's something happening in this case, namely there is a chiral mode, right, attached to this. So if this is, say, still the kx direction, I can sketch the whole span structure now in kx. There's energy. So somewhere there are bulk bands. You don't have to worry about them. That's why I draw them in blue. Then there are the surface states, which are now gapped out. Of course, they are filled up if you project on everything. These are the surface states. And now, since we have a change in the surface mass across this hinge, there would be a chiral mode attached to the hinge for one cone, but now you have two cones, so there is another chiral mode going the other way as well. And they are, of course, now related by time reversal symmetry, and in fact, they even have opposite inversion mirror eigenvalues, like plus and minus I. So they're really protected from hybridization, again, by the same argument as the Dirac cone was protected by hybridization. So now these two modes, they are living on this hinge here, and they go in opposite directions. So this is a Kramer's pair of modes. It's exactly the same electronic structure that you would find on this edge of a 2D quantum spin Hall effect. And of course, the argument was initially perturbative, so I said, okay, I make a weak kink in this surface, but I can make it stronger and stronger. It doesn't matter as long as I retain the mirror symmetry. So that angle here basically is not, doesn't need to be small. Okay. Yes?
Why do you invert how do you invert the mass?
It's basically, so you can think of if you think of the surface Dirac Hamiltonian, there is a perturbation that you can write that opens the mass gap because I break mirror. And in general, this will just be linear in the amount of mirror breaking. Yeah? And the mirror breaking is really like the tilting of the plane. And so if I tilt it the other way, I get the same parameter, but like, in the other direction. That's okay, there's more microscopic ways of deriving this, but like as a simple heuristic way. Okay. That was the first TODI. Let's go to the second one. The second one is much simpler, I think, or somewhat simpler. So here you see that this is an integer classification because basically the number of these Kramer's pairs of modes here, they would be proportional to Cm, or they would be equal to Cm mod over 2. Yeah? Cm over 2 is equal to the number of hinge Kramer's pairs. So it's an integer classification. Now maybe actually Flores' comment is also useful to remember. If I forget about mirror symmetry now and like keep the gap on the surfaces, this would become a C2 criterion because only the Kramer's pairs are by time reversal are locally protected. But you know, when you start with 3 hinge Kramer's pairs, you can, if you break mirror symmetry, you can make them 1, but you can't make that 1 disappear unless you actually make a gap closing on the surfaces. Okay. So now, second example is a higher order TI from inversion, from time reversal and inversion. And here I am connecting to what I said about the C2 topological insulator, where I said that we have to count, if we have inversion symmetry, we have to count the number of band inversions that we have. And actually this is not quite, I mean, that's correct, but there's actually more information in the number of band inversions than just the C2 property. I can define a quantity, let me call it kappa, where I just count the number of bands with plus eigenvalue under inversion minus the number of bands with minus eigenvalue under inversion. So number of, or let's say Kramer's pairs in occupied bands with plus inversion eigenvalue. So this this basically counts the number of band inversions, this kappa, yeah? And what I want to argue, or it turns out that this thing is not defined modulo 2 as the Foucault criterion suggests, but it's actually defined modulo 4. And so let's go through these 4 possibilities. Kappa equal to 0 is, of course, a trivial insulator. Kappa equal to 1 or 3 is odd number of band inversions. It gives you a topological, it's C2, 3D, conventional topological insulator with the surface Dirac cone. And now the interesting case is kappa is equal to 2. So for instance, 2 band inversions. And that gives us this higher order topological insulator. So you could, for instance, if you think about the Brillouin zone, you have 2 Kramer's pairs of occupied bands. So if that's like, you know, Kx, Ky, Kz, and then if you mark the eigenvalues, so minus, minus, and here you get plus, plus. Okay, let's say that's pi plus, plus. Everywhere else you have plus, plus. Yeah. So this would be a situation that I'm interested in. Yeah, you have two band inversions. If these are 2 Kramer's pairs that are occupied, you have 2 minus 1 inversion eigenvalues at one trim, and the others are all plus, for instance. Okay, so why is this so? I should motivate that, and I have enough time to do. And we're going to motivate this from what we know about topological insulators, 3D topological insulators. So we consider the case kappa equal to 2 as a superposition of 2 3D TIs. Okay, and let's think about them as being completely decoupled. Okay. And now we're going to analyze this from a surface perspective, if you wish. So we'll later see that, or in the end, we can relax this condition that they are decoupled, and once we've established that there's some topological surface states, we can just see that they are explicitly not depending on the fact that these systems are decoupled. Okay, so if we have two decoupled but superimposed topological insulators, then of course on the surface, what we'll have is two Dirac cones, right? So, so a surface two Dirac cones. And let me choose a specific realization of the surface Hamiltonian for this. So let's say we say kx sigma y minus ky sigma x. Then there's these are sort of now a 4x4 matrix, right? Kx sigma y minus ky sigma x. So this is what I presented you before as the surface theory of a Dirac Hamiltonian, of a 3D TI, and now I'm just taking two copies of this. But now, of course, the only local constraint on the surface that we have is time reversal symmetry, right? So T in this case would be represented by I sigma y 0, 0, I sigma y times complex conjugation. And in principle, I should now be able to gap out these two surface states without breaking time reversal symmetry because there's only one 3D TI. So, so there should be at least one mass term that I can add to this system. What's interesting, however, is that there is not just at least one mass term, there's just exactly one mass term, okay, that is compatible with time reversal symmetry. So there's only one mass term. And what I mean by mass is in the sense of the Dirac equation, a term that I can add here that, of course, commutes with time reversal is constant and anti-commutes with these kinetic matrices so that it actually opens a gap. And so what is this mass term? It's given by some coefficient times this matrix I sigma z minus I sigma z 0. So you see that this is time reversal symmetric. Sigma z anticommutes sigma y, but I is also flipped to minus I, so this is commuting with time reversal. And it actually, if you check it explicitly, it's anti-commuting with this kinetic part of the Hamiltonian. So the spectrum is really a gapped Dirac equation. But so that's time reversal symmetric. But now we should remember that we are interested in a system that's time reversal and inversion symmetric. And now that's the big point. Inversion symmetry does not restrict what we can put locally on this Dirac equation. So this, we don't have to worry whether this mass term by itself is inversion symmetric or not, because inversion would map one point on the surface to a completely different point on the surface. But what it does, of course, do then, it relates the value of this mass term between different points on the surface. So let's consider a spherical version of this insulator, which is certainly inversion symmetric, as a geometry at least. And let's consider this with a finite mass term on one point here. It's given by m. Now, if I go through the analysis, what I would find is that inversion actually maps m to, well, actually m of x maps to m minus m of minus x. Or, in other words, a configuration of masses is inversion symmetric if on opposite sides of the sphere m has opposite sign. Okay, so if I have m there, then on the inversion related side here, I should have minus m. Good. And Now that has an important implication because I have a sphere, but I have only one real mass parameter to tune, and that real mass parameter has to change sign. So that means that somewhere on the sphere, I have to have a path that this is the wrong color. To have a path where m has to go through 0. Yeah, that's unavoidable. It has to change sign. And now we know what happens in such a situation. Again, this is just two Dirac equations. So we know that the domain wall between the region with positive and negative m binds two modes. And in this case, because of time reversal symmetry, again, they are counter-propagating, and they are a Kramer's pair. Yeah. And so what we can say now about this higher order topological insulator is that it has a protected 1D hinge mode, that's how we call it now, that goes somewhere around the system. Different, however, from the case with the mirror symmetry, we don't really know where that mode is. So there's no, from the bulk, no principle that tells us exactly at which boundary components this hinge mode resides. We could, wobble this line as long as we keep inversion symmetry, and everything is fine. But yeah, so that's how things are. And maybe just as a last remark that this, so now, this only requires inversion and time reversal symmetry. So the fact that these, in the bulk, for instance, these two subsystems were decoupled, we can now relax that, forget about it, as long as we don't make a bulk gap closing phase transition, the system is stable, and the only topological characterization that we needed is this double band inversion here, okay? So, good. Maybe as a closing remark, one thing is that this band structure is realized in bismuth, even though that's not really an insulator. But if you kind of forget about the fact that there's an electron in a hole pocket, you would find this double band inversion. And more broadly speaking, these kind of classifications have now been extended to all kind of space groups and so forth, so that you know which topological invariants to use in which symmetry class and so forth. Okay, good. I'm done. I thank you. No, I get a question.
Just one question. From the definition, so you calculate the parity for your form. When you do, you get an higher order TI. Are you saying that all the weak TI is, 3D weak TI are all higher order TI?
That depends on your point of view. So the weak TI, of course, requires translation symmetry to be protected, right? If you break translation, there's no surface state. Here, I didn't ask for translation. So so if you start with a weak TI that has double band inversion, you break translation, you get a higher order TI. If you don't break the translation, you have no gapped surfaces. So that's, or like some surfaces are not gapped, so you have to live with that. So it's a bit of a matter of how you view it. But yeah, there's no contradiction. It's just that you might end up with gapless surfaces if you have translation symmetry. Right? Yeah.
On your previous example in the roof case, where you invert the mass and the side of the roof, then you draw only one Carroll inch mode, with plus and minus I eigenvalues. How can you resolve this plus or minus I structure?
I didn't explain that to you. If you look at, for one, you know that the whole thing should be time reversal symmetric. So you know that if one is plus I, the other has to be minus I, because time reversal pairs, these are two time reverse partners. Time reversal is anti-unitary, so it sends a plus I eigenstate to a minus I eigenstate. So that's how you know. And then which one is plus and which one is minus is actually a microscopic detail that depends on the surface determination, I think. Oh, that's not actually, no, that's not true. Sorry, that's wrong. This is given by the bulk Chern number, yeah. So which way that thing goes is actually not freedom, yeah.
Are there more questions? If not, let's thank you for